I'm the Philosophical Bachelor, and today I'm going to continue my metaphysical investigations with Chapter 2, Cosmology. The beginning is a misnomer since there was no beginning. Space was always already there. Even if this space was empty, it was still there. But was it empty? According to the Big Bang theory, it was not. In the time prior to the Big Bang event, all matter and energy that will ever exist was already in existence, albeit concentrated in a singular point. Recall how Hume tells us that all knowledge is either relations of ideas or brute facts. If we accept the Big Bang theory, its singularity is a brute fact, making how the singularity got there somewhat beyond question. It simply was there. There must mean somewhere. It was suspended in space. Space must then not be empty since it contained the singularity. Yet general relativity tells us that space-time itself unfolded with the Big Bang's cosmic inflation, not existing prior to the Big Bang. In the singularity, space-time was so curved that it basically enfolded itself, and within it was all matter and energy. That it was already all there is another brute fact, making it also somewhat beyond question. To ask where it came from seems illegitimate. In any case, the position that all matter and energy was already existent is a much easier proposition to consider compared to the position that they came from nothing. The latter is what has puzzled thinkers for millennia, how it is possible we have stuff all around us if, at first, there was nothing. The most common solution is creatio ex nihilo, creation from out of nothing. In its first book aptly named Genesis, the Christian Bible writes, "In the beginning, God created the heaven and the earth." While such creation accounts solve the immediate problem, it kicks the proverbial can down the road, since it leads the inquisitive to ask, who created the Creator? The biblical answer is that the Creator God has always been and always will be in existence. He is eternal. But if there can be things that have simply always been there, such as God, would it not likewise be possible that the stuff that makes up the universe was also simply always just there? If it was always just there, then to speak of a beginning is plainly incorrect. Must there really be a point when and where everything began, or is it merely a prejudice that for something to exist, it must have commenced at some point in the past and then continue to exist, perhaps developing, to its current state in the present? Another prejudice we have to reckon with is how at first there must be nothing, after which some work is done to create something. Both these prejudices derive from our experience with induction to link events together. For instance, just like we are used to the idea of the beginning of the school or work day, the beginning of a new diet or fitness regime, or of a new life in the form of a newborn baby, we tend to think that all things and events must have a beginning in time and an end. Similarly, one may at first not have a house, but after stacking bricks on top of one another and putting in the wiring and plumbing, we now have a house. We started with no house and ended up with a house after adding in materials and effort. Thus, we may think that at first there must be nothing, after which some actions lead to something, forgetting that the raw materials for building were already existent. Another reason for the latter prejudice is that nothing seems to be a simpler state of affairs compared to if there were things. The inductive reasoning here is that things often begin as simple and then become increasingly complex. For instance, the evolution of animals or the education of the young, where they learn basic foundational concepts first, and then later on more complex ideas which build on the basic concepts. However, this prejudice is off the mark, since to go from nothing to something is by no means simple compared to going from something to something else, which is what the Big Bang Theory posits. The Big Bang Theory posits as a brute fact that all the ingredients for the development of the universe, both in terms of matter and energy, were simply just there, concentrated at a dense point for who knows how long before who knows what triggered the rapid cosmic inflation 13.8 billion years ago. I have already explained why it is not quite the beginning, so we need a new term for that point in time. Let us just call it T0, and when we discuss a time before T0, we can refer to that as T minus. Before we discuss possible triggers of the Big Bang, we should consider the opposing possibility to the plenitude of the singularity, that in ancient T minus, a time far in the past from T0, there was only a void so extensive and so completely empty that we should honor it with a capital V. The void was a cold and empty place, theoretically at a temperature of absolute zero. Temperature is a function of the kinetic energy of atoms and molecules. Since there were supposedly no atoms, molecules, and energy in the void, X hypothesis, the temperature in that void will be at the very minimum possible, absolute zero, which is 0 Kelvin, equal to minus 273.15 degrees Celsius. Yet even in a space such as the void, there will be some truths that will hold in it. These truths are truths that are eternally and universally true, such as the truths of logic and mathematics. These truths are those Hume will consider as relations of ideas, and Immanuel Kant will consider as a priori, meaning that they do not depend on experience. Logic is based on two fundamental and self-evident principles, the principle of identity and the principle of non-contradiction. The principle of identity states that A equals to A. What a thing is what a thing is. The principle of non-contradiction accompanies this closely and is equally fundamental. What a thing is not what it is not. That is, A is not equal to not A. The reason why such a priori truths hold true in the void is because they do not depend on the existence or the non-existence of anything, not even space and time. They are always true even if there was nothing, even if space and time did not exist. Does space and time exist in the void? Gottfried Wilhelm Leibniz argues that if space is where objects can be placed, the relative positions of objects then suffice to define the space between them. Since X hypothesis, there are no objects in the void, there is no relative space. If space is, however, a venue where things can happen, such as objects possibly taking up positions within it, then absolute space exists. Newton's argument for this is to consider what happens when objects in a space are removed from it. The space itself does not vanish. In a space where there are objects, they occupy space relative to one another, and this relative space exists within absolute space. Similarly, if time is merely a way to keep tabs on the sequence of events, then time exists relatively. The counter is that so long as a sequence is possible, time exists even if there is no actual sequence, making the existence of time absolute. Since there are X hypotheses no events in the void, as there are no objects, relative time does not exist there, but absolute time does. The argument for this is similar to Newton's argument for absolute space. Even if there are no events, time itself does not vanish. If there are events, then they have a sequence, and hence time relative to one another, but that relative time exists within the absolute flow of time. The debate on whether absolute time and space exist continues in the form of whether space-time is absolute or relative. My theory, however, does not depend on the status of the absoluteness of space, time, or space-time, since the void does not remain empty forever. I only raise the issue because if there exists absolute space, time, and space-time, I cannot see why the void will not have them. If, however, as implied by relativity theory, space-time only comes into existence as the universe itself unfolds, then the void will not have space-time. So far, we have established that the void has a priori truths, space and time, if space and time are absolute, even if they are devoid of content. How about the laws of physics? Would they apply? As the term physics implies, the laws of physics govern physical objects and phenomena such as forces and energy. If that is all physics is, then to speak of gravity or the weak and strong nuclear and electromagnetic forces is premature, since they all only come into play when there are bodies, atoms, and energy, which are supposedly absent in the void. Until such time when atoms and energy appear, the laws of physics will be dormant, if not altogether absent. However, even if the void was the state of space during ancient T-minus, we know today from the evidence of our experience that it did not remain that way, since there now exist physical objects. Hence, we can infer that from the emptiness of the void must have come forth matter and energy. How is that possible since, as Aristotle tells us, the ancient Greeks posit that nothing comes from nothing? I have argued that a priori truths, absolute space and time, exist in the void, and the laws of physics may have to await the arrival of matter and energy. The void, while empty of physical content, is not, however, devoid of possibility. Possibility and nothingness are not antithetical. While nothingness contains nothing, this also means that it can be filled with anything whatsoever, making nothingness a venue for unlimited potentiality. The Tao Te Ching says, "The hub of a wheel has 30 spokes converging on it, but its empty hole is what makes the hub useful for the cart. The vessel is made of clay, but its empty hollow is what makes the vessel useful. A room has doors and windows, but its empty space is what makes the room useful. An object needs matter for it to exist, but its emptiness is what makes the object useful." It may seem paradoxical, but nothingness can be productive. If there is no empty space, things cannot come into it. A cup without its matter of ceramic walls will not be a cup. However, a cup that has no hollow, no emptiness bound by its walls, is also not a cup, since it will not be able to function as a cup, which is a vessel to hold liquids. A completely solid cup may have the appearance of a cup, but not its essence, since it will not be able to hold liquids. It is a cup's hollow, its emptiness, that gives it its ability to hold liquids, and is what makes a cup a cup. However, unlike the cup, in a pure emptiness such as the nothingness of the void, there are no walls, no barriers, since barriers would then be something and not nothing. That means that a void is open to being populated, though once that happens, its nothingness is obliterated, since there is now something in its place. The populating of nothingness with something can happen in two ways. The usual way is from the outside, the way you can fill a cup with liquid from outside it. But in ancient T-minus, the void was all that there was. There was no outside of the void, which contains stuff which could then penetrate and populate it, because there was simply no outside. The void was infinite in expanse. That means that whatever stuff must have come from inside the void. The question thus must be how something can come from nothing. I had already pointed out two possibilities. The first is creatio ex nihilo, where a creator God creates something from out of nothing, but that then raises the question of who created God. The second is the creatio ex materia, where the ingredients of matter and energy already were there. This is a strong contender, where the presence of this stuff is a brute fact. Creatio ex materia theories include the Big Bang theory, but also cyclic universe theories, where the universe undergoes endless cycles of expansion and contraction, a Big Bang leading to a big crunch, which then leads to the next Big Bang ad infinitum. Quantum field theory presents a third possibility, which is a variant of creatio ex nihilo, but a true nihilo this time, where something can really come from nothing. No creator deity required. Quantum objects are objects so small that the laws of classical mechanics, such as those governing gravity and electromagnetism, do not apply to them. Instead, their behavior is described by the laws of quantum mechanics. Such objects include atoms, ions, and subatomic particles. Quantum is the grammatical singular form of quanta. While it may seem that energy is continuous, it is instead transmitted in packets of specific amounts or quanta according to quantum mechanics. At the quantum level, quantum objects exhibit wave-particle duality, meaning they can behave like a wave of energy or like a particle depending on the experimental conditions. Quantum field theory is an extension of quantum mechanics incorporating special relativity. It tells us that pairs of virtual particles and their antiparticles continually flit into and out of existence. These pairs arise because of random quantum field fluctuations even in a vacuum. The particles and antiparticles, being oppositely charged, are usually short-lived as they mutually annihilate and vanish back into nothingness, which is why they are called virtual particles. Mass is conserved since particle A and its antiparticle not A still equal to nothing, the way 1 plus minus 1 equals to 0. Conservation of energy does not rule out random energy fluctuations, which are how virtual particles come into existence. Fluctuations mean that energy states at a point may be momentarily higher or lower than the rest of the field, even in a vacuum. When the virtual particles annihilate, the energy from the annihilation returns to the vacuum, leaving a net zero effect. On rare occasions, however, an event takes place that prevents the recombination and subsequent annihilation of a pair's component particle and antiparticle. What can this event be? One frequently cited possibility posited by Stephen Hawking is that one of the particles gets sucked into a black hole, leaving the other one outside with no counterpart to recombine with. If you do not find that too fanciful, then my suggestion will not seem too outlandish either. For instance, between the space of the first pair, A and not A, another pair comes into existence, and then another simultaneously or in rapid succession, such that A and not A are so far separated by these walls of particles that they lose their force of mutual attraction through the separation of distance, leaving behind the two particles A and not A. Another possibility is that particle A reacts with particle B, forming a new entity AB. Since AB is not of opposite charge to not A or not B, AB is no longer able to be annihilated by either. This leaves three particles in existence, AB, not A, and not B. As these rare occasions that leave behind things compound over time, in all their permutations, they result in a world of things. Hence, from nothing can come something, at least according to quantum field theory. Recall the X hypothesis, The void is an empty and cold space devoid of all matter and energy. It is empty because it contains no matter, and it is cold because there is presumably no energy. Do quantum fields permeate such a space? Consider how even the coldest possible temperature of absolute zero does not imply a complete lack of energy. Recall that the temperature of a space is a function of the kinetic energy of particles in that space. At absolute zero, these particles have no kinetic energy. That is, they have zero velocity, according to classical physics. Both the positions and the velocity of motionless particles are seemingly known with certainty, since they are stationary. Yet, according to Werner Heisenberg's uncertainty principle formulated in 1927, these two conditions of position and momentum being the product of mass and velocity, cannot both be precisely known at the same time for quantum particles. The more certain we are of a particle's position, the less certain we are of its momentum, and vice versa. Hence, according to quantum mechanics, particles even at absolute zero will still have zero-point energy, a vibrational energy they retain under these frigid conditions. But why? What is the source of this Heisenbergian uncertainty? At the quantum level, particles may behave like waves of energy and waves like particles. This is known as wave-particle duality. Constrained in a space so small as to limit its motion as much as possible, the surface of a quantum particle like a photon will appear fuzzy compared to our understanding of a particle in classical mechanics, which has a well-defined surface. This fuzziness is because a quantum particle is spread out over space like a wave, such that it in fact occupies a range of positions as opposed to one fixed position, the way we understand particles to be in classical mechanics. Because of wave-particle duality, a quantum particle is really a packet of waves, each wave with its own frequency and hence velocity. So a particle in fact has a range of velocities and hence a range of momentum. If we try to pin down its precise position, we will then be uncertain as to its velocity, since there is a superposition of waves with different velocities in that position. If we try to pin down its exact momentum, we will be uncertain where it is, since it is in a range of positions at that momentum. This uncertainty is not just a problem of measurement. Even if there are no measurements being made, the wave-particle dual nature of quantum particles means that we cannot know with certainty at the same time all the defining parameters of a quantum particle. This leads us to another expression of the Heisenberg's uncertainty principle, where the shorter the time interval, the more uncertain is the amount of energy in a space. What all this amounts to is that even under conditions of vacuum, at a temperature of absolute zero, which are the conditions of the void, there can be very brief random fluctuations in its quantum field, leading to quantized excitations in the field, which are manifestation of pairs of virtual particles. These pairs of virtual particles may then be separated, leading to actual particles, which are precursors to the matter of the universe. This brings us to our first principle. From nothing can come something. The point of this chapter so far is to demonstrate how two opposing positions, whether the universe at ancient T- was a void, or whether it already had all the matter and energy just waiting to be unleashed in the Big Bang, can lead up to the present universe. The former may even have led to the latter, according to physicist Edward Tryon, who proposed that all the matter and energy of the singularity first manifested as virtual particles in a vacuum. The generation of virtual particles has not ceased and continues to take place everywhere, in spaces that are occupied as well as in vacuums. We know this to be true since the Casimir effect can be observed when two uncharged mirrors are held facing each other very close together in a vacuum. This close separation will exclude virtual photons of wavelengths longer than the mirror's distance of separation. Because there are more virtual particles outside the plates than between them, the forces from the collision of the external virtual particles on the outside surfaces of the plate will be greater than the forces from the collision of the internal virtual particles on the inside surfaces of the plate, leading to a resultant force pushing the plates towards each other. Earlier, I mentioned how a priori truths can exist in the void, such as logical truths. I suggested that the laws of physics may not apply if physics applies only to matter and energy, since there are none in the void. However, if there are fields in the void, then the laws of physics governing fields, such as quantum field theory, will apply. The science suggests that there are fields in the void simply because quantum fields are a fundamental property of space itself. Quantum mechanics supports this hypothesis because during a very short interval of time, we cannot be certain about the amount of energy in a space, according to Heisenberg's uncertainty principle. If, however, space-time does not exist in the void, and hence there are no quantum fields, and there is in fact no void, then we are left with the alternative of how something was already there in T-, which then led to the singularity. We do not know the answer. Many learned thinkers are of the belief that space-time unfolds as the universe expands based on general relativity, meaning space-time was all rolled up in the singularity of the Big Bang, and to speak of what was before that is mistaken since there was no space-time to speak of. Yet other thinkers suggest that there is a larger space that the world formed from the Big Bang is a part of. As our scientific knowledge stands today, we do not know what, if anything, was there before the Big Bang. The question is a question of the ontology of space-time. If there exists absolute space-time or only relative space-time. Do events require a space-time for them to take place in, or is space-time itself manifested when events occur? It is akin to a stage play. Does a play require a stage for it to be performed? Or is it that where a play is performed, that place becomes then the stage? This question has been posed in the history of thought in various ways prior to Einstein's general relativity. As earlier noted, Newton and Leibniz, who were contemporaries, were already debating it. The presupposition that Newton made was that a stage was required, for otherwise where will a play be staged? Before them, René Descartes had famously written cogito ergo sum, or I think, therefore I am. The idea is that an I is required to be the stage or venue for thoughts. Almost a century later, Hume proposed that all that the I or the self is nothing but a bundle or collection of different perceptions, one that needs no underlying thinker to have thoughts. In a similar vein, Hannah Arendt pointed out that the ancient Greek conception of a polis or city-state is not its physical location. It is the organization of the people as it arises out of acting and speaking together, and its true space lies between people living together for this purpose, no matter where they happen to be. This is why, wherever you go, you will be a polis. A community is often characterized by its geographic location, but what truly constitutes a community is its people. Even if they had to relocate elsewhere, if they remained together, they still form a polis. Does the ontology of reality require a stage, an already existent absolute space-time, or does space-time itself come into existence in relation to reality as reality unfolds? Nonetheless, whether at first there was nothing or already something, both scenarios present difficulties. The former being whether space-time itself existed, such that quantum fields can then subsist, the latter being how that something got there. They are currently undecidable, awaiting further discoveries to demonstrate it definitively. In any case, both scenarios involve randomness, the former relying on the random fluctuations of the quantum field in the void to generate virtual particles, and the latter relying on a random event that triggered the Big Bang to happen at t0 instead of a time before or after that. Is the trigger itself a random event? If t0 was not a random point in time but a point of critical buildup of matter and energy triggering the Big Bang event, the Big Bang's cosmic inflation should have led to a uniform distribution of matter and energy in space. The cosmic microwave background is evidence of this uniformity on large scales, but it is, however, not perfectly uniform. The temperature of the microwave background radiation is 2.7 kelvins, with a variation of 0.00003 kelvins or 0.001% across space. More significantly, there are macroscopic variations in the world, such as the multitude of galaxies that are not replicas of one another scattered across empty space. We can account for both sets of variations through quantum fluctuations. In the case of the microwave background variance, it is a direct effect of the fluctuations of the quantum fields pervading space. As for the formation of galaxies, quantum fluctuations amplified by cosmic inflation led to areas where there is a higher density of matter. The effects of gravity then caused these areas to further gather matter, and over a long time led to the formation of galaxies. Both scenarios of an initial nothing or something can lead up to our current generally stable world, with its laws of science in physics, chemistry, and biology considered exact at the macro scale. The ancient Greeks already had a similar idea. Hesiod, one of the two preeminent ancient Greek poets, the other being Homer, writes, "In the beginning there was only chaos, the abyss, but then Gaia, the earth, came into being." This brings us to the second major principle. From randomness can come order. These are the first 4 sections of chapter 2. I'll leave the remaining 2 sections for my next video on cosmology next week. Thank you for listening to the Philosophical Bachelor.